Hello guys, welcome to Physics Grad. In this video we are going to continue studying about the Lagrangian for a system of particles, and previously we stopped at the form of Lagrangian for a system of particles, which looks like this: T minus U, where T is the kinetic energy and U is the potential energy. This can be written as summation half MAVA square minus some function u, which depends on the position alone. Okay, now this r vector, let's call it as Ra. This can be written as three components, in terms of three components in the coordinates, in the Cartesian coordinates system, and I'm going to call it as XA, YA and ZA. Okay, now what will happen, how will this Lagrangian look like if we write these position vectors in terms of the generalized coordinates? As we have already seen in the video on constraints, using generalized coordinates helps us to reduce the number of independent variables in the problem. Okay, and that's what we are going to try to do. Okay, so in terms of the generalized coordinates, okay, I'm going to represent them by Q vector, which denotes all the generalized coordinates Q1, Q2 up till Qs, where S is the degree of freedom. Okay, then every component of the position vectors, for example XA, can be written as a function of these generalized coordinates, and I am going to call this as FAX of Q1, Q2 dot 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 Qs, or FAX of Q. Alright. Similarly, we have YA is equal to FAY of Q and ZA equal to FAZ of Q. Okay. Then what is going to be XA dot? XA dot is defined as dxa by dt, which can be written as follows. This will be dou FAX by dou Q1 into dQ1 by dt plus dou FAX by dou Q2 into dQ2 by dt. So this is the chain rule from of partial derivatives, and I'm using it over here, and so on, plus dot 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 plus dou FAX by dou Qs dQs by dt. Okay, this can be written as summation over some value variable k dou FAX by dou Qk Qk dot. Okay, because this is Q1 dot, this is Q2 dot, and so on, Qs dot. Alright, so that means we have XA dot as follows. Similarly, we will have YA dot equal to summation over some other summation over k dou FAY dou Qk dot, and ZA dot will be given by summation over k dou FAZ by dou Qk dot. Okay, fine. Then how can we represent half MAVA square? So this will be clearly half MA times XA dot square plus YA dot square plus ZA dot square. Okay, which is, so if you consider xa dot square, this will be summation k dou fax by dou qk dot into summation some other variable I dou fax by dou qi into qi dot. Now these two are the same thing. Just to avoid confusion, I am going to denote the summation over two different variables k and I. So this can be written as a double summation over I and k dou fax by dou I dou fax by dou k, so dou qk into qi dot qk dot, right? So in a similar fashion we can write ya dot square and za dot square, and therefore we will have half ma va square is equal to summation over I and k half ma into qi dot qk dot times dou fax by dou qi dou fax by dou qk plus dou fay by dou qi dou fay by dou qk plus dou faz by dou qi dou faz by dou qk. So all I have done here is substituted the corresponding forms of xa dot square, ya dot square, za dot square, and I have taken qi dot qk dot common among all of them. Okay, so this is the expression that we get. Now if you notice, these particular values, okay, except for the qi dot qk dot, these only depend on the values of q. Okay, so this part is dependent only on q, because each of these fax, fay and faz are functions of q alone, and taking a derivative with respect to qi qk is still going to give us a some function of q itself. So I am going to call this as gik, or okay, since it is for the eighth, this is the kinetic energy for the eighth particle, so I am going to call this as gaik of q. Okay, so a represents the eighth particle, I and k is to represent the variable with which we are differentiating or partially differentiating. Okay, so we finally get half ma va square is equal to summation over ik half gaik, which is a function of q alone, into qi dot qk dot. Okay, so this is what we get. But the t that we have in our Lagrangian is a summation over all the values of a. Okay, of ma square. So this is a summation over a half so this will be summation over a. If we substitute this, summation over ik half gaik q times qi dot qk dot. Okay, so this is same as summation ik summation a half gaik q times qi dot qk dot, which in turn I can write it as summation ik half ikq qi dot qk dot, where gik of q is nothing but summation over a gaik of q. Okay, so basically I have called this particular thing as gik. So here it was gaik, here it is gik. Okay, so finally what do we have for our T, form of T? So the kinetic energy T is finally of the form which is given by half summation ik gik of q qi dot qk dot. Okay, so let's stop here and stare at this equation for a moment. And so this is the kinetic energy, and still we see that the kinetic energy is quadratic with respect to the velocities, because there are two velocities multiplied here, so it's quadratic with respect to velocity. But now it has a term which depends on the value of q, right? So initially we had T equal to summation over a MAVA square. This was independent, so this form was independent of RA, but this form is dependent on Q. Okay, so therefore in terms of the generalized coordinates, T is still quadratic, okay, quadratic function of velocities, but it may depend on coordinates also. All right, so that is something that is important to remember. Okay, so therefore finally we will have the Lagrangian, which is T minus u, to be of the form summation half summation ik gikq times qi dot qk dot, okay, minus u of q. Okay, so this is the Lagrangian for a closed system in terms of the generalized coordinates. So this is for closed system in terms of generalized coordinates. All right, now what if the system is not closed? Okay, so what if the system is not closed? So by this it means that the particles which constitute the system is interacting with the particles which is outside the system. Okay, so that is the meaning of system not being closed. So what will the Lagrangian look like for such a system? Okay, so to understand this, let's consider a system A, okay, which is not closed and therefore interacting with system B, okay, which is executing So the system B is executing a given motion. So what do we mean when I say system B is executing a given motion? So this given motion implies we already know how the system B is moving. Okay, so this implies that we know what is QB of T. Okay, so that is the meaning of knowing how the B is executing a given motion. Okay, which means we know how all of its coordinates vary with time. Okay, then how do we find the Lagrangian for a system A which is interacting with this system B? Okay, so to do this we will use the following approach. Okay, so we can look at, so this thing, there is another way of looking at it. So we can look at it as, okay, A is moving in a given external field. Okay, so A moves in a given external field, okay, due to B. So what does this mean? So when the particles which constitute the system A is interacting with particles which constitute the system B, okay, we can look at it as if the interaction of the particles inside the system and outside the system, we can look at this as if we just have the system A which is kept in some external potential, okay, and the value of this external potential will depend on how these particles move. So now there are no particles, but instead I am replacing the effect of these particles by some external potential function. So that is the meaning of this statement. Okay, so to know how A moves, that is our end goal, and that's what finding Lagrangian helps us to solve. Okay, so to know how A moves, we need to find LA. That is how we know how A moves, because once we find LA, we can apply the principle of least action and get back the equations of motion, and from where we can determine how A moves. Okay, so this can be done. So this can be done using the Lagrangian for A plus B. That is, when you take A and B as a whole system, a whole closed system. Okay, so if you write the Lagrangian for L and B, A and B, and by replacing QB, so this Lagrangian of A plus B will definitely depend on QB, which is the generalized coordinates of the system B. Then once we get the Lagrangian for A and B, we simply replace, okay, we replace QB by QB in terms of T. Okay, so for example, if QB is T square, just an example, then wherever there is QB in L, we replace that QB by T square. Okay, so this is a function of time. So if we do that, what will happen? So the Lagrangian for both the system taken together is going to be the kinetic energy of system A, okay, plus the kinetic energy of system B minus some potential function which will depend on the position of both A and B, right? So since we already know QB as a function of time, So we know QB of t. Then we simply replace QB by t in this expression, and we will get L will be equal to TA times QA dot plus TA QB of t QB dot of t minus U of QA QB of t. Okay, so now what we have basically done is we have replaced QB by the appropriate functions of time. Okay, then if you do that, this is going to have the following form: QA dot. Now since this whole thing has become a function of time, because QB and QB dot are functions of time, this can in turn be written as a derivative of some other function. Okay, so TA dash, or a better notation, TB. So TB dash, or TB1 I will call it. Dash it will get confused with differentiating. So I can write this as TB1 of the function, some function of t, because when I combine these both, this t, this should be TB. So this TB is going to be a function of t alone. So I'm going to write this, if I integrate it, I'm going to get TB1, and again differentiating TB1 back, I'm going to get TB. So I can represent this in this form. So this is d by dt of TB1 of t minus U of QA and t. So what I have done here is that QB is expressed in terms of t. Okay, so this, for example, can be AT square plus BT plus C. Okay, then U will just be QA, will be dependent on QA and the variable time, and that is what I have written here. And from our previous lecture, we know that this Lagrangian is equivalent to LA dash, which is TA QA dot minus U of QA t. Because Lagrangian, which is deferred by a total derivative of some function of time and coordinate, is mechanically equivalent, because we are going to get back the same equations of motion. And this, by doing this, we have basically written the Lagrangian as a function of QA dot and t, which is nothing but the Lagrangian for the system A. Okay, so there is no information about B at all in this particular form of the Lagrangian. So we can call this as LA. Okay, equivalent to LA. So therefore we have LA is the kinetic energy which depends on QA and QA dot minus U of QA and T. Okay, so a system which is not closed is can be explained in terms of an external potential. Okay, so by external, the external factor comes from the dependence on time. Okay, because if it was only dependent on QA, then it will depend only on what are the different positions of the particles inside system A, and that will give you the Lagrangian for a closed system. But if this system is kept in such a way that it interacts with some particles outside the system, It is another way of looking at the same thing would be to keep the same system in a potential field which varies with time in the same way as how it would have varied with respect to change in coordinates of the particles of system B. Okay, so that is what we have written here. Okay, so therefore motion of a system in external field, okay, is still described by the Lagrangian of the form T minus U, but U is now explicitly dependent on time. Okay, and that is what we have derived here. Alright, so I hope you have understood what I have taught in this video. See you next time.